Hi everyone. Today we are going to start with the fourth module, the quantum mechanics and laser. Start with, we are going to start with quantum mechanics. And before entering the quantum mechanics topic, we should know why we need quantum mechanics when there was a Newtonian mechanics. This Newtonian mechanics, generally we call it as classical mechanics. This Newtonian mechanics, it failed to explain the energy distribution in the spectrum of black body radiation. This is where the Newtonian mechanics failed, and we are in need of another theory or another mechanics that can explain the energy distribution in the black body radiation spectrum. Before entering into that, we should know what is black body. It is the one which absorbs all range of electromagnetic radiation that incident on it, and once it gets heated up, it emits all kind of electromagnetic radiation it has absorbed. So coming to this is how the black body radiation is at a given temperature. Let us take at T is equal to 600 Kelvin. So at the given temperature, the energy density I have taken along y-axis and the wavelength is along x-axis. At the given temperature, the energy density increases, the value of energy density increases as the wavelength increases. And at one particular wavelength, it reaches the energy density value, reaches its peak. Then as further increase of wavelength will make the energy density to decrease. And we can observe that at different temperatures, the experiments were carried out, and as the temperature increases, the energy peak, the peak of the energy density value shows a blue shift on the wavelength scale. That is, it shifts to the lower wavelength side. And this was explained by number of scientists like Stephens, Vanes, Rayleigh. All those laws failed to explain the energy distribution in the black body radiation. And in 1900, Planck, he came up with a concept called quanta, and he explained the black body radiation based on the concept of quanta. He assumed the black body as made up of large number of oscillating particles, each is vibrating at its own possible frequency. And each atomic oscillator absorbs or emits energy as a discrete units, which is called as quanta. The quanta, it is nothing but the packet of energy. So it absorbs or emits the energy in discrete units, which is called quanta, when it transits from one quantum state to another quantum state. And the oscillators have a discrete set of energy, which is an integral multiple of finite quantum of energy, which is given by En is equal to E suffix n is equal to n into h nu, where h nu, it is the energy corresponding to the packet of energy quanta, and n, it is an integral multiple which ranges from 1 to 3. And next, the energy distribution in the black body radiation is given by Planck in this way. U nu d nu is equal to 8 pi h nu cube by c cube into 1 by exponential of h nu by kt minus 1 into d nu. So this is how the quantum mechanics comes into play. And quantum mechanics, so this is the idea gave birth to the quantum mechanics. And quantum mechanics, it becomes a major branch of study to investigate the mechanics behind the atomic and subatomic world. The major difference between the quantum and the classical mechanics is that the quantum mechanics can be applied to microscopic bodies. To apply the mechanics involved in microscopic particles, we need the quantum mechanics. With the help of classical mechanics, we cannot discuss the mechanics that is involved in microscopic bodies. So the classical mechanics, obviously it is applied only to the macroscopic particles. Whereas the classical mechanics, they are deterministic in nature. But the quantum mechanics, it will be probabilistic in nature. Now, let us enter into our syllabus. The quantum mechanics in our syllabus starts with wave-particle dualism. We know that the radiation can have two properties, two nature. Like it can take a wave nature as well as particle nature. So radiation as a wave that can be explained by the phenomena like interference, diffraction, polarization and so on. Same way, the radiation as a particle can be explained by photoelectric effect, which you might have studied. Photoelectric effect, Compton effect, Zeeman effect, all these phenomena explains the particle nature of the radiation. Likewise, Louis de Broglie, he came up with an idea, he came up with a hypothesis stating that as radiation can exist in two forms like wave and particle, the particle can also exhibit wave nature. That is what his hypothesis states. Since the nature loves symmetry, if the radiation behaves as a particle under certain circumstances and as a wave under certain other circumstances, then one can even expect that entities which ordinarily behaves as a particle also exhibit properties that are attributable to waves under appropriate circumstances. So the particles, the waves that are associated with the particles, we call that as matter waves or de Broglie waves, or even it is also called as pilot waves. So to find out, as particle is taking a wave nature, we are supposed to find out what is its wavelength. So de Broglie wavelength, to calculate the de Broglie wavelength, to derive the expression for it, we are going to consider a photon which is having a mass m and moving with a velocity c. Now, according to Einstein's mass energy relation, we can express the energy of the photon as E is equal to mc square, E is equal to mc square, and by quantum mechanics, we have said that it is nothing but the quanta is nothing but the packet of energy, that is h nu. So E is equal to h nu, which is equal to hc by lambda. Now I am equating these two. So it is mc square is equal to hc by lambda. C will get cancelled out and we will be getting lambda is equal to h by mc, where mass into velocity, it is nothing but the momentum of that particle. So we can write lambda as lambda is equal to h by p, where p, it is the momentum of the photon here. Now with this expression, we are going to discuss the characteristics of de Broglie waves. Right. So we have the expression lambda is equal to h by p, where h is the Planck's constant. So to discuss the characteristics of matter waves, we are taking this expression lambda is equal to h by p. Here we can see that p is nothing but m into c, where m is the mass of the particle and c, it is the velocity. Here we have taken photon, so c is the velocity of photon. If we consider some other particle, it is going to be h by m into v. So here we can see that the lambda, it is inversely proportional to the mass of the particle. So we can say that massive the particle is, smaller will be the wavelength. That is one of the characteristics. Next one, the velocity, about the velocity. If we say if we consider if we say v is equal to 0, that is the particle is at rest. If we consider the particle is at rest, this is going to be 0. Anything by 0 is going to be infinite. So we will get lambda tends to infinite. So lambda tends to infinite, which is not possible. The same way, if we take v as an infinite quantity, right, the momentum also tends to infinity, and anything by infinity will give you 0. So lambda will tends to 0. So it's these two conditions states that gives you the conclusion that the particle exhibit the matter wave one and only if the particle is in finite motion. If the particle is at rest, lambda is infinite, which is not possible. And same way, if it is having infinite velocity, then we cannot calculate the wavelength. So in both the cases, this is not acceptable cases. So we can say that the particle exhibit the matter wave one and only if the particle is in finite motion. The third characteristic is, that is the property of the matter wave, is if we see the expression, the final expression of it, here it is not dealing with the charge of the particle. So as it is independent of the wavelength, as it is independent of charge of the particle, we can say that the matter waves are not electromagnetic waves. And next one, the fourth one is the matter waves, they propagate in the form of wave packets with the velocity called the group velocity. So these four are the properties of the matter waves. Next one, we are going to derive the de Broglie wavelength for an accelerated electron. So for that, we are going to consider an electron which is moving in an electric field, which is having a potential difference of V, and the mass of the electron, let us take it as m, and charge of the electron as E, and it is moving with a velocity V. Now the energy required by the electron in that electric field is given by E is equal to E into V, that is charge of the electron into the potential difference, and its kinetic energy is given by half mv square. Now equating this is completely going to be its kinetic energy. As we said, only when it is in motion, it will have the wave nature. So, we are going to equate both. EV is equal to half mv square, and I am going to multiply and divide by m in the denominator and numerator and denominator. So, it is m square v square. So, m square v square, m into v, it is momentum. So, p m square v square, so it is p square divided by 2m, and p square in terms of de Broglie wavelength, if we write, it will be h square by lambda square divided by 2m. So, lambda square from this expression, if we find out lambda square, it will be h square by 2m EV. So, lambda is going to be equal to h lambda is equal to h by root of 2m EV, or else we can write it as lambda is equal to h by root of 2m E. Thank you. The remaining part we will see later. Thank you.